convection heat transfer. In this particular mode of heat transfer, the flow of the fluid occurs naturally due to the density changes arising out of temperature rise or temperature fall. Supposing if you take a vertical wall like this, the flow of air would be like this. There is again a boundary layer development. Here outside the boundary layer velocity is 0, and at the wall also velocity is 0. Here also Newton's law of cooling holds good. The rate of heat transfer by convection is equal to HA delta T HA TW minus T infinity watts. In free convection or natural convection, H is function of G beta delta T L mu rho Cp K. These are all the variables that would influence the value of convection heat transfer coefficient in free convection or natural convection, where fluid has been moving by virtue of its density changes. There is no external agency to provide some velocity to the flow. There is no agency like fan or a pump or a blower in the case of the natural convection. Whereas in forced convection, there is a fan or a blower which provides some velocity to the air so that it can blow over the plate and it could take away the heat at a quicker rate. In free convection, obviously, we can expect that the rate of heat transfer is low. Beta is a coefficient of isobaric volume expansion coefficient. This is change in volume by original volume at constant pressure. In the differential way, you can write dou V by dou T into 1 by V at constant pressure. For ideal gas, if gas is ideal like air, beta value will be 1 by capital T per Kelvin. Remaining all are same as thermophysical properties. Mu, rho, Cp, K are thermophysical properties of fluid. Same as in the forced convection. This is mu is in Pascal second, dynamic viscosity, rho is in kg per meter cube, Cp is in joule per kg Kelvin, and K is in watts per meter Kelvin, thermal conductivity of fluid. G is acceleration due to gravity. Delta T is the temperature difference between the body and the fluid. L is the characteristic dimension of the body. Maybe diameter. If it is a circular tube, in such cases, D becomes the characteristic dimension. If it is a hot horizontal plate like this, where the fluid will be moving, in this case, the length of the plate becomes the characteristic dimension. So, based on the shape of the body, the characteristic dimension L or D would change. Here also, from dimensional analysis, that is Buckingham pi theorem, we can say that Nusselt number is a function of GR and PR. Here in free convection, GR replaces Reynolds number of forced convection. So in forced convection, Re will be there. In free convection, Gr, Grashof number, will be there, where Gr is Grashof number, defined as inertia force into buoyancy force divided by viscous force whole square. The Grashof number is given by G beta delta T L cube by mu by rho whole square, which is G beta delta T L cube by nu square. Nusselt number, as expected, it should be HL by K. PR is property of the fluid, that is mu Cp by K. So in any free convection problem, Nusselt number should be a function of GR, PR. In empirical correlations for natural convection, Nusselt number is usually given as C into GR PR to the power of N. The product GR PR is also known as Rayleigh number. Now I shall do a small matching problem regarding dimensionless numbers. List 1, this is list 2, this is process, this is predominant, parameter, associated, in process. Left hand side is mass transfer, B is forced convection, C is free convection, D is transient conduction, that is unsteady state conduction. Right side, number 1 Reynolds number, number 2 Sherwood number, number 3 Mach number, number 4 Biot number, number 5 Grashof number. How do you match the things? For forced convection, obviously the answer is, for B, the answer should be 1. For C, answer should be, free convection should be Grashof number 5. For D, the answer transient conduction, the answer should be 4. Then what about mass transfer? For A, it should be Sherwood number. In fact, Mach number would appear only in compressible fluid dynamics, or when the velocities of the fluid is very high in the range of velocity of sound, then the Mach number plays predominant role. Particularly when the compressibility effects of the fluid is taken into account, then the Mach number comes into play. Or high density changes, high pressure changes are involved, where the shock waves are formed, Mach number plays crucial or predominant role. Now I shall give the empirical relation for laminar flow through pipe. This is flow. If Reynolds number is less than 2000, implies laminar flow. For constant wall heat flux, Nusselt number in laminar flow, Nusselt number is calculated by 48 by 11, that is 4.364. Whereas for constant wall temperature, for fully developed laminar flow, Nusselt number is given by 3.66. We may conclude that Nusselt number for a tube wall temperature, for a tube whose wall temperature is kept constant, is 16% less than the similar tube receiving a constant wall heat flux. Here, note can be noted that Nusselt number for a tube whose wall temperature is kept constant is 16% less than that of a similar tube receiving a constant wall heat flux. Multiple choice question. I do it now. Next time I do a multiple choice question. The non-dimensional parameter known as Stanton number ST is used in A. Condensation heat transfer, with the laminar film layer, B. Natural convection heat transfer over flat plate, C. Unsteady heat transfer from bodies in which internal temperature gradients are neglected, D. Forced convection heat transfer in flow over flat plate. Here the answer is Stanton number is used in the forced convection, because Stanton number is nothing but Nusselt number by Reynolds number into Prandtl number. It is used in the Reynolds-Colburn analogy, that is the similarity between fluid friction and heat transfer. In that analysis, Stanton number comes into picture in forced convection over flat plates. In fact, in unsteady state heat transfer, Biot number is talked about. Natural convection heat transfer, Grashof number is talked about. I shall solve another objective question. Nusselt number for fully developed turbulent flow in a pipe is given by Nu is equal to C Re to the power of A Pr to the power of B, where Re and Pr are Reynolds number and Prandtl number respectively. The values of A and B are A is equal to 0.5 and B is equal to 0.33. For heating and cooling both, B A is equal to 0.5 and B is equal to 0.4 for heating and B is equal to 0.3 for cooling. C A is equal to 0.8 and B is equal to 0.4 for heating and B is equal to 0.3 for cooling. D A is equal to 0.8 and B is equal to 0.3 for heating and B is equal to 0.4 for cooling. Here Reynolds number, it is a fully developed turbulent flow. Reynolds number index should be 0.8. For heating, B should be 0.4 and for cooling, B should be 0.3. And answer is C. And C, the index, the multiple C in the equation is nothing but 0.0. The answer is option C, and the C value in that equation is nothing but 0.023. Now I shall do a problem on natural convection or free convection. A metal plate 0.609 meters high forms the vertical wall of an oven and is at a temperature of 161 degrees Celsius. Within the oven is air at a temperature of 93 degrees Celsius and 1 atmospheric pressure. Assuming that the natural convection conditions hold near the plate, estimate mean heat transfer coefficient and rate of heat transfer per unit width of plate. The solution to this problem could be given like this. The film temperature TF is equal to 161 plus 93 divided by 2, that comes to 127 degrees Celsius or 400 Kelvin. Properties of air at 400 K are nu is equal to 26.4 into 10 power minus 6 meter square per second. Alpha is equal to 38.3 into 10 power minus 6 meter square per second. What is this alpha? Thermal diffusivity. Thermal conductivity K is 33.8 into 10 power minus 3 watts per meter Kelvin. Prandtl number is equal to 0.69. And isobaric coefficient of volumetric expansion is equal to 1 by Tf could be calculated. Mean film temperature, that comes to 0.0025 per Kelvin. The nature of flow may be known by calculating a Rayleigh number. What is Rayleigh number? Product of Grashof number and Prandtl number. Here the Rayleigh number RAL is given as GRL PR, that is G beta L cube delta T by nu into alpha. In fact, PR, where PR is given by mu Cp by K or nu rho Cp by K. Grashof number is given as G beta delta T L cube by nu square. If we substitute these two values, we get a Rayleigh number. These two are the formula for Prandtl number and Grashof number. Therefore, Rayleigh number is calculated as 9.81 G value, beta is 0.0025, L is 0.609 whole cube, delta T is 161 minus 93 divided by 26.4 into 10 power minus 6, that is new value. Thermal diffusivity is 38.3 into 10 power minus 6. This comes to 3.72 into 10 power 8. Implies flow remains laminar. So from laminar, from correlations, from free convection correlations, empirical correlations, for laminar flow, for in case of vertical valve, it is given that Nusselt number is 0.68 plus 0.670, Rayleigh number to the power of 1 by 4 divided by 1 plus 0.492 by PR whole to the power of 9 by 16 and whole to the power of 4 by 9. it comes to 71.87. Therefore, average convection heat transfer coefficient, that is given as NUL average into K divided by L. It is 71.87 into thermal conductivity is 0.0338 divided by 0.609. It comes to 3.988 watts per meter square Kelvin. This is well in the range. Usually in the case of the free convection in air or gases, the values of H values will fall between 3 to 25. Therefore, the rate of heat transfer per unit width is given as Q is equal to H bar L, and the unit width has been given L into 1 into temperature of the wall minus temperature of the fluid. That is 3.988 into 0.609 into 161 minus 93. It comes to 165.18 watts. This is the rate of heat transfer per unit width. Hence the problem.